So let's do that just by reviewing some of what we know. Based on our energy diagram that we've developed, we know that the same starting materials, an alkyl halide, which I'm going to represent with Rx, and a nucleophile / base, can lead to substitution products via an SN2 reaction. And for example, an example of an SN2 product would be something like this, where you get one possible enantiomer. We know that it proceeds with via backside attack with inversion of configuration. In terms of the rate, we know that it's fastest for primary and methyl alkyl halides, slower for secondary alkyl halides, and then no reaction for tertiary alkyl halides. And we know that it's favored by good nucleophiles whose pKa's are conjugate acids, with conjugate acids whose pKa's are greater than 0. So those are some of the basic principles of the SN2 reaction, and the reason why tertiary alkyl halides don't work is because of sterics. Another thing to recall in the SN2 reaction is that the nucleophile attacks the alpha carbon whilst the leaving group leaves. All right. Your text points out that good leaving groups can accelerate SN2 reactions, but good leaving groups can accelerate E2 reactions and SN1 and E1 reactions, so it's not really a great decision point, and we won't worry too much about it at this stage. The competing elimination reaction that's also, I guess, one other thing we want to say about SN2 is that it is concerted, that is, the nucleophile attacks while the leaving group is leaving. Elimination reactions via E2 give us products where the base has removed a proton and the leaving group leaves, and we form a new pi bond between alpha and beta carbons. We've got the so-called Zaitsev rule that tells us that the major product is the most stable alkene. And we know that trans alkenes are more stable than cis because of sterics. We know that more substituted alkenes are more stable than less substituted alkenes because of hyperconjugation. In terms of how the rate of E2 depends on the substitution of the alkyl halide, this is maybe something that you've read, but we haven't mentioned a lot in class. E2 is actually very fast for tertiary alkyl halides, in part because the alkenes you make from tertiary alkyl halides are more stable and more substituted, but also because tertiary alkyl halides have more beta protons to choose from. So it gets faster from a statistical standpoint. For secondary alkyl halides, it's okay. And for primary alkyl halides, it's way slow. And then I guess it is favored by good bases, and we've defined good bases as molecules whose conjugate acids have pKa's greater than or equal to 16. So you can see a challenging situation if you use a molecule that's both a good nucleophile and a good base. With a secondary alkyl halide, you're going to have the chance to compete between SN2 and E2 reactions because they both have reasonable rates for secondary alkyl halides. In contrast, if you've got a tertiary alkyl halide, it doesn't matter whether whether your base is also a good nucleophile because SN2 is simply not an option. And then if you had a primary alkyl halide, it turns out SN2 will be fast enough to totally outcompete the E2 reaction for primary alkyl halides. Okay? Then our other option is leaving group leaves first, that is a rate determining step. You get a carbocationic intermediate. And this process of leaving group leaving first is not observable, or doesn't happen. I don't know how to abbreviate that. Not good for primary alkyl halides, because primary carbocations are too unstable. It's okay for secondary carbocations, secondary alkyl halides leading to secondary carbocations, and it's better for tertiary alkyl halides leading to tertiary carbocations, but still not fantastic. It's still uphill in energy. But once you get to that carbocationic intermediate, you've got perpetual and inevitable competition between SN1 and E1. SN1 is attack of the carbocation at the alpha carbon to make a substitution product, which, supposing that we had a starting material like this and we used methanol, which is neither a good nucleophile or a good base, you have to wait for the leaving group to leave. You get the carbocationic intermediate, and then in the product you get both possible configurations for your substitution products. So this first step, leaving group leaves, will be better for tertiary alkyl halides, but in general you won't even go here if there's another option. And so weak nucleophiles / weak bases have to wait till the leaving group leaves. Things that are both weak as nucleophiles and weak bases have to wait until the leaving group leaves. Then they can react. The E1 reaction involves attack at the beta proton and then forming a pi bond. So E1 products in this case would look exactly the same as the E2 products. So just by comparing products, it would be difficult to tell whether the reaction had been E1 versus E2. Okay. Questions so far about that summary? That's what we got going on. Yeah?
And what is the pKa requirement for the conjugate acid for the E2 reaction?
Same as, there it is. It's favored by good bases with pKa's greater than or equal to 16. Yep. Good. Others? Yeah.
Within E1, does the same major rules apply that is for E2?
Yes, that's right. A good question. For E1, the same rules apply for major versus minor. The more stable alkene is the major product. You've got steric factors to consider, and also the fact that more substituted alkenes are more stable because of hyperconjugation. All right. So in the study guide, you can consider lots of different combinations of these reactions. I think about it this way, and I found it useful. You may not like to order your thoughts this way, and that's fine. We've got 3 different kinds of alkyl halides and 4 different categories of nucleophiles. We have the good nucleophiles that are also good bases, and that is their conjugate acids have pKa's greater than or equal to 16. We've got good nucleophiles that are nevertheless weak bases. This is conjugate acids with pKa's greater than 0, but less than 16. And then we have weak nucleophiles that are good bases, and this is because of steric hindrance. There are some examples described in your text, tert butoxide, some other sterically hindered bases that have acronym names, DBU and DBN. You don't need to memorize those structures. And then we have molecules that are neither good nucleophiles nor good bases. And these tend to be molecules whose conjugate acids have pKa's less than 0. So let's talk through each of these options, and we'll do maybe some easy ones first. The weak nucleophiles and weak bases have to wait for the leaving group to leave. So what do you suppose happens for a primary alkyl halide? Whole lot of nothing. Right? That's just dissolving your molecule, dissolving your primary alkyl halide in like water or methanol. There's basically nothing to see here, folks. But for secondary alkyl halides, are carbocations reasonable intermediates? Sure. And so we would expect to see SN1 and E1 products for secondary alkyl halides. Same thing for tertiary alkyl halides. The weak nucleophile / weak base waits for the leaving group to leave, and then you get a competition. Yeah?
Would a methyl alkyl halide have the same thing as a primary?
Yeah, good question. We'll group methyl alkyl halides in the same category as primary alkyl halides. Yep, others? Okay, another easy one is the good base that's not a good nucleophile. Then substitution is off the table, and by virtue of the fact that it's a good base, it won't wait for the leaving group to leave. I'm drawing an example of a sterically hindered base, but there's also those other ones, DBU or DBN. Those are abbreviations that you don't need to memorize, but might see on a practice exam or something. E2 is your only option in all of these cases, because you're not going to do SN2. Now, on problems that I give you, you won't expect any competition for SN2 with these sterically hindered bases, even for the primary alkyl halides. Of course, methyl halides can't do elimination, so that's that. But of these available options, primary, secondary, or tertiary, if you were to start to see substitution products, where do you think it would happen?
The primary?
Yeah, with the primary or the methyl. So if you get in the lab someday, we're going to pretend like it's cut and dried, but if you get in the lab someday and you use tert butoxide and methyl iodide and suddenly make tert butyl methyl ether, and you wonder what the heck happened, Dr. Price told me there was no SN2 for these sterically hindered bases, and I will tell you the world was more complicated than I told you. I'm sorry for oversimplifying. All right. The next two are sort of the troublesome categories. Let's start with the molecules that are good nucleophiles. No problem there for primary alkyl halides. Good nucleophiles that are weak bases aren't going to do elimination, so this is actually pretty straightforward, SN2 alone. For secondary alkyl halides, SN2 as well. Again, weak bases aren't going to remove beta protons first, and these molecules have the option of doing SN2, so they'll take it. It's only when you get to the tertiary alkyl halide that you can't do SN2, and so you have to wait for the leaving group to leave, and you're going to see the competition between SN1 and E1. And then lastly, for things that are both good nucleophiles and good bases, we're going to have to worry about competition for the secondary alkyl halides. However, for the tertiary alkyl halides, there's no SN2, and for the primary alkyl halides, SN2 wins over E2. So that summarizes the observations and the things that you've read in chapters 7 and 8. With those tools in mind, and with our detailed understanding of the mechanisms of these reactions, we are now equipped to try a bunch of challenging practice problems and see what we can do. Questions, though, before we move on? Yeah.
Wait, so for a weak nucleophile and good base that's a methyl, it would have to be SN2?
Let's see. I'm sorry, a weak nucleophile that's a good base. For the methyl, yeah, and in fact, that's why I didn't put methyl on the list, because there is no E2 for methyl halides. So, and in fact, methyl halides are easy. They're just always SN2, because you can't form carbocations and you can't do elimination reactions. All right, other questions? Yeah.
What does the pKa say about the weak nucleophile and good base?
It doesn't. There's no pKa limit there. You're looking for sterically hindered bases. Generally, they're strong. They do generally fall into this category of conjugate acid with pKa greater than 16. But the thing that makes them bad nucleophiles is just because of sterics. Okay, others? Yeah.
So the good nucleophile and weak base column, just trying to understand, because the nucleophile trends pretty much mirror our base trends, like a strong base will pretty much be a strong nucleophile. But in this case, just trying to understand why we can have a weak base, is that because if we're not above 16, our base isn't strong enough to pull off a hydrogen, because the carbon-hydrogen bond is very strong, right?
Uh-huh.
Very low in energy, so is that why we consider them weak bases at that point, because they're not strong enough to pull off that hydrogen?
Yeah, so let me just rephrase the question for folks at home who may not have heard it. How can a good nucleophile also be a weak base? And part of it has to do with, we've made these categories based on experimental observations. So it may be that there isn't any first principles reason other than what we've observed. Second, the terms good and weak are always relative. So notice that we've set the cutoff line for weak base versus strong base at conjugate acids with pKa's of 16. Weaker than what? Weaker than hydroxide. So are you strong enough to deprotonate an alcohol or water? If you are, you're likely strong enough to remove beta protons. In contrast, for good nucleophiles, we can do the pKa comparison, but what we observe in actual reactions is that the limit is quite a bit lower. And the characteristics of good nucleophiles are generally molecules with lone pairs on heteroatoms, negatively charged. Large and polarizable atoms tend to be good nucleophiles as well. Things that have pKa's that are greater than 0. And that includes a lot of items that are on, I'm worried that I've made a mistake there. That includes a lot of items that are on our list of good bases as well, like hydroxide and methoxide. But what we're saying is there are some nucleophiles that don't appear to be competitive in removing beta protons, but nonetheless give reasonable reaction rates for attacking alpha carbons. So it's empirical. It turns out I learned when I taught my 552 advanced OChem class that there are parameter values for good nucleophiles, somewhat like pKa's. But I forget what they are, and it was too complicated, apparently, for me to understand, so I decided not to talk about it. Okay, others? Sure.
For the good nucleophile and a weak base, for the white tertiary bond, how come E2 can be possible, or E1 can be possible when it's a weak base?
Okay, that's a good question. Good nucleophile but weak base. How come SN1 and E1 is possible? Once you get to that carbocationic intermediate, the acidity of those beta protons goes way up because they're next to a positive charge. And so now the requirement for a strong base drops away. Any base is enough, even the weak ones. So very low pKa for that beta proton. Okay, good questions. Others? All right, so let's just do some challenging example problems. The way to learn this is to just make tons of mistakes and then figure out why you made them. So let's work on this one. I apologize if this is something you've seen before. I'm taking it out of my notes, and we can make up others as we go along. And we can even use the same starting material and then swap out what the nucleophile will be, nucleophile/base, and see whether that changes our observations. Okay, I kind of like this one. Let's use potassium cyanide as our nucleophile. Now, some of you are going to get tripped up on that because nucleophiles are negatively charged, but this shows a nucleophile with its counter ion. And some of you are going to say, well, I don't know what to do with that counter ion. I don't know if it participates in the reaction or not. It doesn't. People will sometimes show it above the arrow because you can't buy a bottle of Cn-. The electrostatic force is strong, and anytime you buy an anion, it comes with a cation. And the cation can be important, but we're basically going to ignore it. So if you see KCN or some other counter ion, that's fine. Some chemists will use different counter ions with different purposes and different properties. So if you were going to ask, does it have to be potassium? Could it be lithium or sodium? Don't know. Don't particularly care. I just know potassium cyanide tends to be one that's used. So I'll go ahead and erase that in case it made you uncomfortable, but be okay with the fact that counter ions might show up. Here's the situation: a tertiary alkyl halide and a good nucleophile. Cn- conjugate acid is HCN, and that has a pKa of around 9. So not quite a good base relative to water. So because of that, it's not going to do E2. And because the fact that this is a tertiary alkyl halide, SN2 is not an option. We might want it to be because we've got a good nucleophile, but the alkyl halide is too sterically hindered to permit that. So what's the only thing that happens? We sort of have to wait and wait and wait until we form carbocationic intermediate. Understand this is a high energy intermediate, and so it doesn't form in large concentrations, but as soon as it forms, you have the planar carbocation, and the nucleophile can attack it. Okay, so I'm going to draw what I think is the product, and you tell me what's wrong with it. Am I done? What did I do wrong? There's another product. Okay, what is it? Where cyanide came in from above. All right, so suppose you were on your practice exam or study guide and you made a similar mistake. You might be tempted to look at that and say, okay, I get it. I need to get the Cn- on both sides and then move on. You need to drill down a little bit deeper to analyze why you thought that and why you didn't get that. It's probably, if you drew just this one, it's probably because you thought the mechanism was SN2 and needed to have inversion of configuration, or it's that you forgot that the intermediate is planar and can be attacked from either side. either way, that's a problem that you need to fix. Alternatively, what if you started to draw, so both of these answers are correct, and you would need both of them to adequately communicate that this was an SN1 type reaction. What if you had done this as well and then changed that other stereocenter? Why is this wrong? That stereocenter is not involved in the reaction. And so this looks like you're just grasping at straws. You know that something happens in an SN1 reaction that involves stereochemistry, so you're just going to go for all the options and hope for the best, which gets you partial credit at best, right? So if you make this mistake, that shows an even more broken understanding of the SN1 reaction that you need to fix, okay? Now, I'm hesitant to keep wrong answers in my notes, lest someone say, you showed this as an answer. So I'm going to go ahead and put a big X on that. This is wrong, and then I'm going to promptly delete it. So you can watch the video and see what the wrong answer was, but we'll get rid of it that way. Now, I'm still missing some stuff. What am I missing? The E1s, right? Remember that SN1 and E1, we can't be selective once we get to the carbocation. So it might be useful now to look at the carbocation again and think about the possible reactions. So am I done? Okay, if I just draw that one, it indicates that I know a little bit about what an elimination reaction is, but it probably was that I was in a hurry because there are different kinds of beta protons. We'll color them differently. Right? You got 3 different kinds of beta protons, each of them adjacent to the positive charge. So the one I drew, I guess we could color it red because it came from removal of the red beta proton. If we remove the purple one, we've got this one. Okay, similar but different. I guess that maybe isn't helpful. And then lastly, you've got this option. And if you had to pick among the various elimination possibilities, what do you think is the major one? What do you got? Which one would you expect to be more stable? Go ahead.
The third one?
Third one, which is more substituted and is therefore more stable. And probably the major product. Probably the major elimination product. What I would want you to answer is going to depend on how I ask the question. If I say, which of the following options are products of this reaction, you better include 1, 2, 3, 4, and 5. If I say, which of the following are substitution products of the reaction, that's only 1 and 2. If I say, which is the major elimination product, it's just 5. Now, am I ever going to ask, do elimination products dominate over substitution products? No, because I don't know how you'd predict that. Yeah?
Does it go 5, 4, 3 in terms of like
Well, you know, does it go in this order 5, 4, and 3 in terms of abundance? I can't say anything about absolute percentages. I would guess that the tetra-substituted alkene is more stable than the tri, which is more stable than the di-substituted. But all bets are off in terms of exact percentages. Yeah?
In an E1 reaction,
Right. This is a great point that I want to illustrate. If you look at our starting material and think about protons that can be anti to the leaving group, the purple proton could be the one that's trans to the leaving group, and presumably the red protons on the methyl group could be anti to the leaving group. But, oh, dumb, I drew this in the wrong way. Yeah, and then the blue one actually is trans to the leaving group and could be anti to it as well. So it turns out all three of those are available for an E2 reaction. We don't have to worry about it though, because in this intermediate, the empty p orbital is evenly spaced between the top face and the bottom face. So it no longer matters whether your syn and anti just goes away completely. And now all the requirement is just that you be able to line up with that p orbital. Okay? Why do the dots and dashes become planar after the double bonds are formed? Oh, yeah, why am I not using a wedge for this methyl group? It's because before the methyl group was a stereocenter, now it's just an sp2 hybridized planar carbon. So I can represent its shape without dashes or wedges because it's planar. Yeah? No, you can't, and actually in this case there are no hydrogens on the same carbon as the leaving group. But we could illustrate that with a different thing, like if you were going to do an E2 reaction here, here's the alpha carbon, here are the two beta carbons. No, there's no place for the electrons to go to kick off that leaving group. Like you might think, okay, can I do that? Well, fine, but where's the other lone pair on the bromine going to go now? And so no, the alpha protons that are alpha to the leaving group aren't participating in in an elimination reaction. Okay, others?
Can you just quickly explain how you got that first E1 product?
The first E1 product comes from removal of the red proton, which is beta to the positive charge. And so we remove that proton and we form a new pi bond between what used to be the methyl group and the carbon where our leaving group was. I use the wedge there because that stereocenter is unaffected in this reaction. Same thing here for 4. And then I don't use dashes or wedges here because that carbon is no longer sp3 hybridized. It's just sp2 and flat. Yeah?
Could you please give an example of E2 where the paired planar issue does come into play?
Okay, so we want an example of E2 where the anti-periplanar issue does come into play. Sure, let's take a look at that. I'm trying to see whether this is a good example or not. There was a question on the practice exam, and I forget all of the details, so maybe I'll just go look it up real quick. Nope, that's not the one. Okay. Wonder how well I can remember that. Probably not very. All right, so all right, let's think about, and then let's use a sterically hindered base. This is a secondary alkyl halide. We're using a good a weak nucleophile that is a good base, so probably E2 is our only option. Now, for E2, you're going to look for protons that can be anti to the leaving group. We have done that previously in the context of molecules that were not in rings of any kind. And in that case, we could rotate around carbon-carbon bonds to get a proton anti to the leaving group. In a ring, as you've learned from chair flipping, up stays up and down stays down, and they don't interchange. And so we need to consider for leaving groups in rings whether the available beta protons can indeed be anti to the leaving group. So let's just identify the different kinds of beta protons. You've got the orange one on the orange beta carbon, and then you have purple one, and then a blue one. I'm putting these beta protons, purple and blue, different on the same carbon because they are different. One is on the same side as the methyl group in this other thing. The other is on the same side as the chloro group. So those are two different situations. That's another example of protons that are diastereotopic. Now, let's look at which of the available beta protons can be anti to the leaving group. Are there any that we can rule out as not, or let's see, cannot be anti to the leaving group? Okay, orange one, because it's on the same side, right? And then for that same reason, Hayden at home also notices blue. Yeah, blue is also not possible. So, what is the only E2 product we can get? And if we had a way of telling the difference between blue and purple protons, blue proton would be left and not purple, right? Yeah, go ahead.
It is a little bit of a dumb question. Those two hydrogens that we're saying are equal. Is it because they're in a ring that they can't rotate?
Yeah, these two hydrogens that are not equal, they are in a ring. You can rotate, but you can't ever change up from down. You can make axial equatorial and so on, but you can't interchange up and down. There's no way to swing that all the way around in the ring. Okay. When dealing with six-membered rings, it can be best in E2 kinds of problems to look at the ring from above. We could draw the same ring in a chair conformation, and you might be tempted to make a error. So here is the methyl group. Actually, let's put the methyl group here and the isopropyl group here. 1, 2, 3, 4, 1, 2, 3, 4, both are up. And then on carbon 2, the chloro group is down. Orange beta proton is here. Blue beta proton is here, and purple beta proton is here. So right now, from our perspective, it looks like none of those groups is anti to the leaving group, right? In fact, if we were to look down the bond between carbon 3 and carbon 2, via a Newman projection. On the front carbon, we would see the equatorial proton, purple proton up, and the axial blue proton down. On the carbon in the back, holy Toledo, Batman, what are we doing there? Ring should have been angled up. On the back carbon, the ring substituent would be there. Chloro would be here. Right now, no proton is anti to the leaving group, right? But if we can flip chairs, we can make it so that if we flip the chairs, we can convert that down equatorial chloro group on carbon 2 to a down axial chloro group on carbon 2. The orange beta proton still can't get anti to the leaving group. The blue beta proton still can't, but the purple one is now anti-periplanar with the leaving group, and you are set for E2. So this is an interesting principle, even if, and it just so happens for the example I chose, of the two possible chairs, the chair and the other chair is the more stable one. But even if it weren't, as long as you can access the other chair, if that's the reactive conformation, the reaction is going to proceed just fine. And that's why I'm saying it might be better, instead of worrying about the chair flipping, to just draw the cyclohexane ring from above. We solved this problem without even considering what the chair was doing. But if I had given this problem to you just like this, and you hadn't thought about going to the other chair, you may have looked at that and said, no protons can be anti to the leaving group, therefore no reaction. Well, actually the purple one can if we go to the other chair. Does that sort of get what we're going for there? Another way to test this question is to, I'm trying to remember where this comes up best. Okay. I've made this a little bit easier because I've made it so one of the beta carbons doesn't have any protons on it. But you've got a proton here and then a deuteron there. D equals deuterium, which is an isotope of hydrogen. And it's something that we can incorporate sometimes in organic molecules as a label, because we can tell, there are ways you can tell the difference between a proton and a deuterium. And it's kind of like putting a star or a smiley face or a label on one of the two protons so you can tell them apart. So I could show you two possible products here, and you would need to pick which was the appropriate one or correct one. What do you think? First one. Why? You're correct. Why would that be? Yeah.
Because the deuterium is anti to the halides and nucleophile.
Right. Let me just repeat that for the folks at home. The deuterium is trans to the halide in this conformation. Now, you may have thought, look at that, nothing's anti to the leaving group. Well, your alternative to defeat that potential distraction is to say, okay, fine, let's go to the other chair where iodide is here, and then deuterium on the adjacent carbon would be down axial instead of down equatorial. Then you've got the anti-relationship that should allow a base to come and remove the deuterium. Yeah. Alternatively, you can sidestep that whole consideration of two chairs by simply drawing the molecule from above. Let's see, putting the iodide here, and then just realizing that, hey, only the deuterium is trans to the iodide, so only the deuterium can ever be anti to the leaving group. Okay? So, if you selected both of these answers, A and B, it could mean that you don't understand that the E2 reaction has to proceed via an anti-arrangement of the beta proton relative to the leaving group. It could be that you were confused by the portrayal of the molecule in a chair conformation, which shows a need for better spatial reasoning. It could also be that you didn't consider whether the beta proton or deuterium could be anti to the leaving group in the other chair conformation. So there's multiple reasons why you might have gotten this one wrong, and only you are going to be able to, as you do practice problems, tease out what that is. But it's going to be key for you to do that and find the transferable skill that you missed that you can take and move on to the future. Because you may not see this exact same problem again. So it's not going to do you any good to say, oh, okay, the deuterium's the one that's there. Okay. No, you got to know why it's there and why you missed it and so on, so that you can apply it in unfamiliar situations. So which conformation is more stable, the first or the second, is a question from home. Deuterium is an isotope of hydrogen. The difference is in the nucleus. The nucleus is a very small part of the atom. The atom size is mostly the electrons. The radius of deuterium and hydrogen is basically the same. So there's no big steric difference there. Either chair has an axial methyl group. So I suppose the first chair would be the more stable one because the iodide, the only other non-hydrogen thing, is equatorial. But it's not more stable by a whole lot. And at equilibrium, you would have not a one-to-one mixture of the two, but something close to it. All right, what else? Oh, time's gotten away from us. There is nothing else. Okay, so that concludes chapters 7 and 8 for us. I have a couple of biological examples of SN2 and SN1 that I think I'll show you and talk about briefly at the beginning of next lecture. Other than that, we'll move on to chapter 9 on Monday. So why don't you finish up your 7 and 8 study guide this weekend? If you want, I'll make it due by the end of the day Monday, because what do I care?